Alright, how's it going? This video here, we're going to look at related rates. Now, I've got around 5 examples I'm going to work here, but I've got a lot more examples on my YouTube channel of just single problems by themselves. You can check those out. I'll put the links to them in the description. So if this is not enough, you can go watch some of those other ones. It's more problems, okay, different than these. Some of them are, a couple of them may be the same as what I'm doing in this video, but I think a lot of them are different. All right, so let's look at the first one. It says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? All right. So when you're doing related rate problems, you've got to come up with a function. Okay, you got to come up with a function, and then you'll have to take the derivative of it, and it'll give you information to plug in, and it'll tell you what to find and all that. So let's go through the problems, and I'll explain all of that as we're working through the problems. All right, so let's see what it's telling us. It says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. So the key here is the volume, okay? So we know we're working with the volume of a sphere, and they want to know how fast is the radius increasing when the diameter is 50 centimeters. All right, so well, we need the volume of a sphere. Well, the volume of a sphere is 4/3 pi r cubed. All right, so there's our function right there. Okay, the volume. That's what we're working with. Now let's look and see the information that it's given us. Now remember, when we're taking the derivative, we're doing these related rates, and we're taking the derivative with respect to t. All right. So it tells us that the volume increases at a rate of 100 cubic centimeters per second. So that tells us how the volume's changing. So remember, the derivative is a rate of change. So what this has given us, it's telling us that dV dt is equal to 100 cubic centimeters per second. I'm just going to write the 100. You can put cubic centimeters per second if you want. Now, also, it's wanting to know how fast is the radius increasing. So we're looking for the change in the radius. Well, see, there's r, your radius, and so I'm looking for dr dt. That's what I want to know. That's my unknown. And we want to know this when r is equal to 25. So you might be wondering, well, how did you get to 25? Or how did you get 25? Well, it says the diameter is 50. So remember, the radius is half the diameter. All right, so now all we have to do is take the derivative of this with respect to t. So I get dv dt is equal to, so now remember the 3 comes down, so 3 times 4/3 is 4 pi r squared times dr dt. And now I'm going to solve for dr dt. See, that's what we want to know over here. We want to know the change in the radius. So if I divide both sides by 4 pi r squared, that's going to give me dr dt is equal to 1 over 4 pi r squared times dv dt. All right. Now, all we do now is plug everything in. See, I'm going to plug the 100 in for dV dt, and I'm going to plug the 25 in for r. And then that'll give me the change in the radius. Tell me how fast it's increasing. And so now I'm going to get dr dt is equal to 1 over 4 pi times 25 squared, plug the 25 in for r, times dv dt, which is 100. And so this is going to give me, well, I can reduce it. That's what, 1 over 25 pi, which that's approximately 0.0127, and then that's going to be centimeters per second, because remember the radius, that will be measured in centimeters. Okay, remember centimeters cubed, that's volume. Centimeters squared would be area. All right, so that's all it is. The main thing, probably the most difficult thing in these problems is going to be coming up with this. Okay, this problem, it was easy because it was the volume of a sphere. Okay, so what's the volume of a sphere? Well, there it is. Now we differentiate it. We take the derivative with respect to t. All right, so let's look at the next problem. It says a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? All right, so the best thing to do here is draw a picture. So let's draw a picture. And I've got a ladder sitting on the wall. All right, let's draw that a little different. Let's draw it like this. Let's label this X. Let's label this Y. That's a right angle, and it tells us the ladder is 10 feet. It says a ladder 10 feet long. So here's your ladder right here, and it's 10 feet long. And they don't give us any dimensions for X or Y. All right. Okay. So let's go ahead and write down the information they give us, and let's write down what we want to find. Okay. All right. So obviously this is 10 feet long, the ladder is. All right. So let's read. It says, if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So that means the bottom here is sliding this way, right here, sliding this way at 1 foot per second. So what is this? What is this? That's the change in X. That ladder's getting further and further away from the wall here. That's how fast X is changing. So they're telling us that the change in X, dx dt, is 1 foot per second. All right. And they want to know how fast is the top of the ladder sliding down the wall. All right. So as this part right here slides this way, away from the wall, this point up here is sliding down the wall. And they want to know how fast is this point right here sliding down the wall. So that's the change in Y. So we're looking for dy dt. That's what we want to find. And we want to find that when what? Sliding down the wall when the bottom of the ladder is 6 feet from the wall. So that's when X is equal to 6. All right. See, it says when the bottom of the ladder is 6 feet from the wall. So when that distance is 6, how fast is this? How fast is it sliding down the wall, the top of the ladder? So we need an equation. All right. So for this one, well, I mean, what do we have? We got a right triangle, don't we? Pythagorean theorem. So x squared plus y squared is equal to 100. All right. So let's take the derivative. So I get 2x times dx dt plus 2y times dy dt is equal to 0. Okay, remember, derivative of a constant is 0. All right, so you may be wondering, okay, so, well, and I might need to change this up. Instead of writing 100, I just went ahead and did that in my head. Let's write it as 10 squared so you can see I did this squared plus this squared equals this squared. Okay, regardless, the derivative of 10 squared is 0. Okay, now you might be wondering, okay, you've got the 10 in here, you plug that in, but how come you didn't plug the 6 in for x? Okay, because that's what they want to know when x is 6. So why didn't I plug the 6 in? All right, so you don't want to plug the 6 in because look at it this way. You see this length right here, this 10 feet for the ladder? As this ladder is sliding out and this point sliding down, this length here is never changing. That ladder is 10 foot. It's not going to change. The length of it is not going to change. So we're plugging the 10 in because that length is constant. It's 10 foot the whole time. But as this ladder is sliding, the distance from the wall to the bottom of the ladder, it's changing. So we don't, x is not 6. Okay, x is not 6. They just want to know how fast is this point sliding down when x is 6. All right, so if things are going on here, all right, like this is sliding down, this is sliding out, when things are going on like that, ask yourself, okay, is this distance changing? Yes, so we need the variable there. Is this distance changing? Yes, so we need the variable. Is this distance changing? No, it's always 10 feet. So we plug the 10 in. All right. Now we need to know what? We need to know what the change in y is. We need to know dy dt. So let's solve this for dy dt. So I get 2y dy dt is equal to negative 2x dx dt. Divide both sides by 2y, so I get dy dt is negative x over y times dx dt. All right, so now let's look and see what we've got. We've solved for dy dt. Now we need to plug x in. Well, we got that. That's 6. We've got dx dt, which is 1. But then we've got y. We don't have y up here, do we? So what do? Well, they want to know this when x is 6. So when x is 6, what is y? Well, that's what 6 squared plus y squared equals 10 squared, right? And so I'm going to get y, y is equal to, what is that? Is that 8, I believe? That's 100. 10 squared is 100. That's 36. 100 minus 36 is 64. Square root of 64 is 8. So y is 8. And so now I'm going to get dy dt is equal to negative x, which is 6 over 8 times 1, which is negative, let's see, what is that? 2, negative 3/4. Okay. And then we are in feet and seconds, so that's feet per second. So it's this point here is sliding down the wall at 0.75 feet per second. The negative is sliding downward. All right. So hopefully all this is making sense. Like I said, the important thing here is coming up with this right here. And then all you're doing there then is just taking the derivative and plugging in stuff. I think the important thing is writing down what's given and what you're wanting to find, and then get your equation. And then take the derivative solve for what you're looking for, and then get everything you need to plug in. Okay, get everything you need to plug in. And look, if you're working one of these, you're going to have the information. You may have to solve for one of them like we did here, but you're going to have the information to plug in or solve for things that you need to plug in. All right, let's look at the next one. It says a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. All right, so first thing we need to do here is draw a picture. So let's draw our cone. All right, and we know this height is 4 meters. We know the radius is 2 meters, and we've got some water right here, okay? And we know from here to here, that's the radius, and from here to here, that's the height. So this would be the radius at any given height of the water, and here's the height of the water, okay? Wherever it is, you gotta see water's being pumped in. All right, so let's find let's write down what we're given, and let's write down what we're looking for. It says a water tank has the shape of an inverted circular cone with base radius 2 meters in height, 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute. Okay, so what does that mean? 2 cubic meters per minute. Now, remember what we're dealing with. We're dealing with the volume of the water, okay? Not the volume of the tank, but the volume of the water. All right? So that's how fast is the volume of the water changing. So that's dV dt is equal to 2 cubic meters per minute. Okay? Find the rate at which the water level is rising when the water is 3 meters deep. So they want to know the change in the height. So we're looking for dH dt, okay? And that is when, let's see, when the water is 3 meters deep. So that's when H equals 3. That's what we're looking for. All right, so we need our equation, okay? So we've got the volume, okay? The volume of a cone, that is 1/3 pi r squared times H. All right. Now, let's look at this. Now you see all the information that it's given us. It's not telling us anything about the radius. Okay? Doesn't give us any information about the radius. This radius here, this 2 meter radius, that's for the tank. That's the radius of the tank. The 4 meters, that's the height of the tank. We're just dealing with the water right here. Okay? So if you look in this problem, nowhere do they say the radius of the water at any particular height. Okay? They don't give us that. But they do tell us when H equals 3. So we know we're going to plug 3 in for H when we take the derivative of this. Okay? We can plug 3 in for H. So somehow we need to get this in terms of H. We need to get rid of the R somehow. Okay? and write the radius in terms of h. So let's see how we can do this. Well, I could write r over h is equal to 2 over 4. So that tells me r is equal to what? H over 2. See, if I multiply the h up here, 2 over 4 is 1/2, so 1 over 2. So remember, I want r in terms of h, just like I have here. And I'm just using similar triangles, okay? This radius over this height is equal to this radius over this height. They're proportional. All right. So what that does is that tells me the volume is 1/3 pi times h over 2 squared times h. And so the volume is, let's see, that's going to be h squared over 4. So that's going to be 1 over 12 pi times h cubed. So that's going to be h squared times h is h cubed. Now let's take the derivative. So I've got dv dt is equal to what? 1/4 pi h squared times dh dt. Now what am I looking for? Well, I'm wanting to solve for dh dt, right? So I'm going to get dh dt is equal to, now, I mean, I wrote it like this, but let me do this. It'll be easier for you to see. Let's see, I forgot what I had written there. Let's see. That's going to be pi. Now let me, hang on. Let me undo that so I can see what I had written there. All right. Okay, so that's pi over 4 and h squared. Pi over 4, h. So that's going to be pi h squared over 4. Okay, I just wrote it like that instead of writing it as 1/4 pi h squared. I just put the pi h squared in the numerator. And so when I solve for dht, I'm just multiplying by the reciprocal. Okay, that's the only reason I rewrote it like this, is so you can see that I'm multiplying by the reciprocal. So that's 4 over pi h squared times dv dt. All right, so that's going to give us dh dt is equal to, now just plug everything in. Look, do I have h? Yeah, that's 3. Do I have dv dt? Yeah, that's 2. And so this is going to give me 4 over pi times, let's see, h is 3, so that's 3 squared times dv dt, which is 2. And so I get dh dt is equal to 8 over 9 pi. And that is, let's see, we're in meters and minutes. So that is meters per minute. And look, if it makes you feel better to write that as a decimal, if you punch that in your calculator, you're going to get about 0.28 meters per minute. Okay, so that's how fast the water level is rising. All right, but that's the whole key to this. That's what I've been talking about in these other problems, is writing this down, what they're giving you, what you're wanting to find. Okay, this right here, see, we've got dv dt, we've got h, but look at our formula. I know when I take the derivative of h, I'm going to have a dh dt. That's what I'm solving for. And then we've got the dv dt. That's the 2. But see, I need h. But this r right here is what was messing me up. So I had to figure out some way to get r written in terms of h, and written in terms of the height. Okay, that's the things you've got to look for. Okay, it's all there. You just got to figure, okay, well, I got to do this, or I got to rewrite it like this because this is what I have to plug in. Okay, so be careful with that. All right. How about this one? It says car A is traveling west at 50 miles an hour, and car B is traveling north at 60 miles an hour. Both are headed for the intersection of the two roads, At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? All right, so basically we've got a car driving this way, and we've got another car driving this way, right? See, one's traveling north, one's traveling west, okay? So there's north and there's the one traveling west. Car A is traveling west, so let's just label this. Well, let's do it like this. Let's label this car A, and we'll label this over here car B. Let's label this X. Let's label this Y. Okay. All right. And we've got this line right here. We'll call that Z. This is a right triangle. All right. So it says at what rate are the cars approaching each other? So you can see as this car's driving this way, this car's driving this way, this right here is changing. It's getting shorter and shorter and shorter, and that's how they're approaching each other. Okay, that's the change in this Z. Okay. All right. So now let's write down what we're given, what we're wanting to find. It says car A is traveling west at 50 miles an hour. So we're traveling this way at 50 miles an hour. So that's how X is changing, right? That's the change in X, 50 miles an hour. So we know dx dt is equal to what? Negative 50. All right. Now, why negative 50? Well, we're traveling west, and this distance is decreasing. Okay, the distance is decreasing, so it's negative 50. And then the same thing with dy dt. Well, that's traveling north at 60 miles an hour. See, the distance is decreasing as I'm heading to the intersection, so that's going to be negative 60. All right, so both are headed for the intersection of the two roads. At what rate are the cars approaching each other? So that's dz dt. That's what we're looking for. And they want to know when car A is 0.3 miles, so when X is equal to 0.3, and car B is 0.4 miles, so that's when Y is equal to 0.4. All right, so we've written down the information they give us. We've written down what we're wanting to find. Now we need an equation. So what's our equation? Well, it's a right triangle. So I've got what? X squared plus Y squared equals Z squared. Okay. See, this distance, and this distance, they're all changing as the two cars are getting closer. See, this distance is changing, this one's changing, and this is changing also. All right. So remember what I talked about earlier. So we're going to have all variables. Remember with the 10-foot ladder, remember the length of the ladder never changed, so we put the 10 in. But all of these distances are changing, so they're all going to be variables. So let's take the derivative. So I get 2x dx dt plus 2y dy dt equals 2z dz dt. And I need to solve for dz dt. So I'm just going to divide everything by 2z. So I get dz dt is equal to x over z times dx dt plus y over z times dy dt. And then we plug everything in. So let's see. dx dt, I've got that. X, I've got that. Z, I don't have z, do I? I've got y is 0.4, and I got dy dt, which is negative 60. So I've got everything except for z, right? I've got everything except for z. All right, so there's our problem. We got to know what z is. Well, I need to know what z is when x is 0.3 and y is 0.4. So I've got x squared plus y squared equals z squared. So let's see, that's what 0.3 squared plus 0.4 squared equals z squared. I believe z is going to be what, 0.5. So there we go. So dz dt is equal to 0.3 over 0.5 times, was that negative 50 plus 0.4 over 0.5 times negative 60. And when we put all of that into our calculator, we're going to get about negative 78 miles per hour. That's how fast the distance between them. That's how fast they're approaching each other. Okay, so they're approaching each other at a rate of 78 miles per hour. Okay. All right, so let's look here. All right, so this is the last one. All right. It says a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? All right, so let's go ahead and draw a picture. And look, this is just going to be a right triangle again. All right, so we've got a searchlight right here, and that is 20 feet from the path. Okay, so we're going to go ahead and label that because, you know, as this man's walking, I mean, this distance is changing. This is going to change because it's hooked on to the end of here, but this is not changing any, is it? This isn't changing because it says it's 20 feet. It's sitting on the ground here. So as this man's walking, this spotlight is just rotating. See that? It's rotating. And so let's see, how about we label this X? Okay, let's label that X. And let's see, it wants to know at what rate is the searchlight rotating. Okay, so it's this right here. See, it's like you got a point right here, and it's rotating, and this is moving as the man's going, and so it's this angle here. That's what we want to know. Get rid of all those dots. But that's what's going on. We're looking at this angle theta. How fast is it rotating? All right, so let's see. It says a man walks along a straight path at a speed of 4 feet per second. So he's walking along the path. So that's the change in x, dx, dt. That's the 4 feet per second. Searchlight is located 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating? Okay, so they want to know how fast is this angle changing? How fast it's rotating, right? Isn't that what an angle rotates? And so we're looking for d theta dt. That's what we're looking for. And that is when what? The man is 15 feet from the point on the path closest to the searchlight. So here's the point on the path that's closest to the searchlight. And we want to know when he's 15 feet away from that. So that's when this distance x is equal to 15. That's what we're looking for. All right. So like I said, we've got to have what? We've got to have an equation, don't we? All right. So in the past, in the other examples, when we had a right triangle, what did we do? We did Pythagorean theorem, didn't we? Well, I don't think that's going to work here because Pythagorean theorem's not going to include theta. So let's see, we've got theta, x is the side opposite, 20, this distance here, that's the side adjacent. So that's tangent theta is equal to opposite over adjacent, which that gives me x is equal to 20 times tangent theta. I just went ahead and solved it for x. Now, I don't think it really matters if you solve for x or not. I just went ahead and did it. So now let's take the derivative. So I've got dx dt is equal to 20 secant squared theta. Remember, derivative tangent is secant squared. And then don't forget times d theta dt. Now, what are they wanting to know? They're wanting to know d theta dt. And so if I divide both sides by this, 20 secant squared, that's going to give me d theta dt is equal to 1 over 20 times 1 over secant squared theta times dx dt. And so I've got d theta dt is equal to 1 over 20 cosine squared theta dx dt. Remember, 1 over secant is cosine. All right. So does it look like we have everything we need? I think so. Let's see. So for dx dt, I'm going to plug in 4. Oh, goodness. Now what about this? Cosine squared theta. Well, let's see. I know that's when x is 15, and I need cosine. So remember, cosine is adjacent and hypotenuse. So I need to know what the hypotenuse is, and I need to know the hypotenuse when x is 15. So when x is 15, that's going to give me, let's see, I got to do x squared. Oh, I'm sorry. I gotta find this side here. So I've got 15 squared plus, and I don't know, we'll call this y. It doesn't matter. You can call it y, z. I'll tell you, let's just call it z. Make it easier. Z squared is equal to 20 squared. So that is going to give me z is equal to, let's see, what is that? Is that 25? Let me double check. It's going to be 20 squared minus 15 squared, 20 squared minus 15 squared, and then I take the square root of that. No, hang on. Let me see something here. Never mind, hold up. That was pretty stupid, wasn't it? Z squared is equal to 15 squared plus 20 squared. Is that better? Look, last problem. I guess my brain's gone now. And so I think that's, let's see, 20 squared plus 15 squared. Then I'm going to take the square root of that. That's going to be 25. So Z is 25. All right. So we've got that. Let's label this. That's 25. This is 15. So what am I looking for? Cosine, right? So look, cosine is what? Adjacent over hypotenuse, which is 4/5. So cosine is 4/5. So see, I can plug the 4/5 in for cosine. I can plug the 4 in for dx dt. So I get d theta dt is 1 over 20 times 4/5 squared times, what was it, 4? Okay, times the 4. And so that, when we plug all of that into the calculator, that gives us, let's see, 0.128 radians per second. And there's your answer. All right. So That's how you do it. See, this one was a little more difficult. Okay, but look, you've got to take all the stuff you've learned from trig and algebra, and you got to bring it all into this. Okay, so we had a little. I don't know what I was thinking when I wrote that down, but anyway, it's fixed. Everything's good now. But yeah, that's it. Okay, that's related rates. Just write down what they give you, write down what you're trying to find, write down your equation, take the derivative, and then just plug all the stuff in. And if you're still watching, remember, I'll have the links to my other related rate problems in the description so you can watch those. I think there's quite a few more examples I do. The baseball, and I think the pulley on the boat. That's one of them, and I don't even remember what other ones, but there's some more. All right, so I hope this video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see you later.